So in this video, we're going to look at the Hardy Weinberg equilibrium and the sort of questions you might get. So you could get asked, for example, a percentage of the population that display a particular trait, or the frequency of a particular allele, be that the dominant or the recessive, or even what's the percentage of a population that are heterozygous for a particular trait. And there are two equations you need to know about this. So we will first of all look at how these equations relate to the gene pool. So if we take this example, it's a made-up population, a very small population, but we can see here the phenotype. So the made-up one, blue hair, is the dominant allele, red is the recessive, and the pictures show the phenotype, so the outward appearance of individuals. So we've got blue hair and we've got red hair. Below, we've got the genotypes of each individual. So those that are homozygous dominant with the blue hair, homozygous recessive with the red hair, and those that are heterozygous, and they display the trait of blue hair as that's the dominant allele. So if we look at the gene pool, we're thinking about each of the individual alleles no longer associated to individuals. So we can see in the population that we've got with our blue and red hair, we have 11 out of the 24 alleles are blue. So that is equivalent to 0.458. We have 13 out of the 24 have red hair. So that gives us 0.542 if we do that division. Now this links to the first equation where we can say P plus Q equals 1. And in this equation, we have P being the frequency of the dominant allele, and crucially that is the allele, and Q is the frequency of the recessive allele. And they are going to equal 1, i.e. 100% of the population. So actually, when we calculated P here, we could have done 1 minus 0.458 to calculate Q, which would give us the same answer. So, using the information we've worked out from the gene pool, we can then think about individual phenotypes and genotypes. So if we're thinking about, first of all, the homozygous dominant, we need to think about the probability from selecting from the gene pool one dominant allele followed by another. Now, we know that the probability of selecting one dominant allele from that gene pool is 11 out of 24, or 0.458. And to get a second one in a row, you need to then have multiplying by the same. In other words, we're multiplying P by P, which equals P squared, and the value we get by doing this calculation is 0.209. On the other side, if we think about selecting homozygous recessive individuals, we need to select the recessive allele followed by another recessive allele. And we've already worked out that that would be 13 out of 24 multiplied by 13 out of 24, which we know the values of, and we can calculate to be 0.294. As we've selected Q times Q, that is equivalent to Q squared. Now, thinking about the heterozygous individual, we can either select the dominant allele first, followed by the recessive, or we can select the recessive allele first, followed by the dominant. We're still getting heterozygous individuals. Now in both those cases, so this one we will have 11 out of 24 times by 13 out of 24, thinking about the frequencies in the gene pool, and this would be the 13 out of 24 times by the 11 out of 24. And what you've got to do, because we can get both of those, we need to be able to add those up. Or in other words, we could say 2 times PQ, or 2PQ. So if we do that calculation, we get 0.496. So That may seem like a lot of maths, but now we can see where the other equation comes when we're looking at Hardy Weinberg equilibrium, because that equation is p squared plus 2pq plus q squared equals 1. So 1 being everyone in the population. P squared is the homozygous dominant individuals, and in this case, it's 0.209. Q squared are the homozygous recessive individuals, and in this case, we know the probability of those is 0.294. And then the only ones left are the heterozygous individuals, 2pq, and we know that's 0.496. So here we are looking at the probability of different genotypes, and you can sense check your calculations that they should add up to 1. Now, this is the equation you need to know and be able to use, because when you've got certain values, you can use the equation to then go the other way and work out the probability of different phenotypes within a population. So now we've had a look at how the equations sort of represent the population, I want to look at a question. So here we've got, in a population of mice, brown fur colour is dominant, so capital B for that allele. And we're told that the frequency of the allele is 0.75. You're asked to work out the frequency of the different genotypes and phenotypes in the population as a percentage. So we know that mice can either be grey and brown, and these are the two equations we need to be thinking of. And I want you, whenever you're thinking about allele frequency, so frequency of alleles, we need to be thinking about P plus Q equals 1. When we then think about genotypes in the population and phenotypes, we need to be thinking about P squared plus 2PQ plus Q squared. So first of all, we're given information about the allele frequency. So that's how we're going to start. So we're told P equals 0.75. So using the equation P plus Q equals 1, we know 0.75 plus Q equals 1. So we can work Q out to be 0.25. So now we have both the P and the Q value, we can work out any genotype we want to. And we're going to use this equation for that. So using that equation, we know that P squared is the homozygous dominant. Okay, plus 2PQ is the heterozygous, and Q squared is the homozygous recessive. Okay, so if we use the equation, we know P is 0.25, so, 0.75, so P squared is 0.75 squared, which equals 0.56, or we're asked to give it as a percentage, so 56% of the population are likely to be homozygous dominant. Using the equation 2PQ to find out the number of heterozygous individuals, we're going to times it by 2, 0.75 times 0.25, and that gives us the answer 38%. And finally, the homozygous recessive, we know that Q is 0.25, so we are going to do 0.25 squared, which gives us 6%. So 56% of the individuals, their genotype, so this is where the genotypes, 56% are homozygous dominant, 38% are heterozygous, and 6% are homozygous recessive. And you should be able to count those up and check they equal 100, sense check your answer. But we're also asked to give the phenotypes. So we know they can be either brown or grey. So brown is going to be the homozygous dominant one and the heterozygous. So we've got 56% plus 38%, 94% of the population are going to be brown and 6% are going to be grey. So that's how you work out the phenotypes at the end. So questions can come at this from a different angle as well. So in this question, we're asked, in a population of 300 people, 72 have blue eyes, which is the recessive trait. Calculate the frequency of the recessive allele in the population. So when we're given information about phenotypes, as we are here, we're going to have to use the equation p squared plus 2pq plus q squared equals 1. We will, when we're asked for allele frequency, go on to have to consider p plus q equals 1 as well. But first of all, let's work out the number or the percentage of people that have blue eyes. So we do 72 divided by 300 have blue eyes, oh not 3,000, 300 have blue eyes. Okay, so if we do that, we get 0.24. Now, that's the number of individuals that are homozygous recessive, so equivalent to q squared. We want to find the frequency of the recessive allele, so we want to find q. So q equals the square root of that, which equals 0.49, or 49% of the alleles in the gene pool are the recessive allele. Okay. Then we go on to be asked, what is the frequency of the dominant allele? So the brown allele. So in this, we're going to use p plus q equals 1. We want to find out p, and we're given, well, we know, I should say, that q is 0.49. So therefore, p must equal 0.51. And if we're giving it in a percentage, that's 51% is the frequency of the dominant allele. The final question, what percentage of the population are heterozygous? Well, we know the heterozygous individuals are 2pq from our equation. So we're going to do 0.51 times 0.49. Okay, and that gives us 0.50 is 50%. Now, it's always useful to double check your answers and sense check them. So I'm going to use this equation to sense check my answers. So we've got p squared plus 2pq plus q squared equals 1. Well, we know that q squared is 0.24. We know that 2pq is 0.5. If we work out p squared, so we know that p is 0.51, so 0.51 squared, okay, that equals 0.26. 0.26. 0.26 plus 0.5 plus 0.24 equals 1. We've sense checked it and I'm happy with my answers. So I hope you found this video useful on the Hardy Weinberg equilibrium and how and when you might use it. But it is really important to remember it's only going to work under certain conditions. So if the organism's diploid, they only reproduce by sexual reproduction, the fact that the generations must be discrete and don't overlap, the fact mating must be random, and the population size being infinitely large, which it isn't in our case. Anything that might change the allele frequency, like migration, genetic drift, mutation, or natural selection, would render this not relevant. So you're only going to use it when you've got a stable allele frequency.